Hey, John here. This is going to be an update on my timing, the VGA sync generator module that we looked at before. The concern is that for the TI video display processor, in order to generate a screen based on your patterns in the generator, the colors, and all this other fun stuff that map into this region of what I like to call the active display region, right, where all the characters go, minus the border, in my opinion, is the active display, okay? Now, in order to get from color bars to that, we need to look at what it means to create a screen that's built up of, an active display with borders around it. And we've already looked at the front porch, horizontal sync, and back porch, but let's look closer at what I did in here. A whole lot of new signals were added. First, as always, a big thanks to everybody that supports my channel, all the likers, subscribers, Patreons, everybody. Thank you very much, especially the VAPs listed here. All right, so what we're going to do is we're going to have a look-see at my VGA sync generator, and we're going to see that I've added a few more parameters and ports to my module to allow us to also emit time information regarding the borders and the boundaries of the active display. All right, a reminder that row 0, column 0 is the upper left corner of with this part out here, we will call the visible display region, okay? Again, we already talked about porch, horizontal and vertical sync, and the back porches, horizontal and vertical as well, okay? So basically the borders start looking a lot like the way the front porch and back porch around the sync worked. If you think about it, if I drew a line all the way down here, this border on the right would be your right border, which would be precede your front porch, your horizontal sync, back porch. The thing to the right of the back porch would be my left border, for example. The top border would look a lot like another porch of sorts, right, that comes after the back porch, and the bottom porch and so on before the front porch. So it should be obvious at this point, thinking of it that way, I hope it's obvious anyway, that when we look at the VGA sync code, we'll just see a few more parameters that specify the sizes of those things, all right? So before we used to have just, how big is the video display, and it was 640 by 480 were my defaults, and the syncs in the front and back porches. So what I've added here was the left border, right border, the front porch is here, horizontal sync, back porch, for all the horizontal stuff, right? Now we've got a vertical top border, vertical video, and a vertical bottom border. These three, I broke the vertical video out into these three separate pieces, okay? And what do we got? Porch, sync, and back porch. So the porches are going to be the same values we saw before because we're just generating VGA here. But we've added these borders, okay? Put some notes up here because we're dealing with my active display region is going to be 512 by 384. It's going to be centered with borders, like this. These default parameters, what does it mean? And we're going to run 640 by 480 by 60 hertz with a 25 megahertz pixel clock. Close enough. Any VGA screen should be able to do that. And I added this note in here, which is a reminder to really punch the fact that where we're heading, remember, the VDP, the TI VDP, is the thing that I'm trying to model for the Nouveau project, is going to be a 256 by 192 active display region, okay? Remember, I call the active display this part in here. Now that means we could either have giant borders with a teeny little active display, which, as a joke, I did one of those at one point in time and just laughed because it makes the active region so small it is utterly worthless. Now what I decided to do is just double this. So 256 times 2 is your 512, all right? 192 times 2 is your 384, or, apply basic algebra and reverse it like I did there. Okay, so what happens is, if I take the VGA pixels and I use a 2 by 2 set of VGA pixels, I get one VDP pixel. Okay, so we're going to just magnify the pixels, the VGA pixels that come out of the timing information out of VGA sync is going to express the screen as defined in VGA pixels, okay? Not in VDP pixels. We'll get to the finite state machine next time, and we'll see that when it runs, it basically ignores, or in a way, it will ignore the least significant bit of the row counter and the column counter, thus dividing those values by 2, so that in the VDP, let's call it a domain, or in the region of the circuitry that concerns the VDP, we'll see that it is moving at half the speed. All right, so it makes the pixels bigger, and it just so happens that 512 by 384 on a 640 by 480 screen, the borders aren't too bad. I mean, there's a waste of space over there, but in order to do a nice simple power of 2 integer division, this works out real nice. You could go down to 0 borders if you play around with other VGA timings and go with like a 4 by 4. You can end up getting it mapped in fine, but then you have no borders. Some games and stuff might use the border color to mean something, so this is the best of a couple of different evils, okay? So, how big are the borders? Well, 64 VGA pixels for the left and right borders. Okay, top and bottom borders are 48 pixels, or rows, we could say, in height. Okay, now this is only 32 when you get over to the VDP, so we're wasting 32 VDP rows, which is a fair number of rows if you think about it, right? That's 4 whole text lines, because you got to take the 32 divided then by 8, gives us the the 8 pixel high pattern size that goes on the screen. So we're wasting 8 would-be lines of text at the top and the bottom of the screen. And what are we at here for the left and right? Well, that is the left and right. It's 8 columns, I should say. The top and bottom is 48 over 2, which is a 24 divided by 8. I don't know. It doesn't come out as conveniently, but, yeah, same sort of thing. What do we got here? 1, 2, 4, 5. I don't know. I'll leave it as a test for the viewer. Never do basic algebra in your head while your mouth is open. A good lesson I should take to heart a little more often on my channel. In any event, what else do we know here? What else is the philosophy we need to understand? Row equals 0 is the first topmost visible pixel row. Okay, the first row of the vertical top border. And that goes back to my comment about this guy here. The very first row, very first column is my origin of this whole display in terms of the the numeric coordinates for the row and column. So 0, 0 is the upper left. So this reminds us of that fact. The very last row, in terms of the timing, when this emits, as you recall, out of its ports, there's a row number and a column number. So up here, I remind everybody that the very last row is going to be the final row of the back porch, and the very last column will be the very last column of the back porch. So it does fit together nicely like this. And this is the same as I think it was before. So the very last column is going to be the last column of the vertical back porch. Very last row is going to be the very last row of the horizontal back porch, okay? Okay, so you got to keep all this in mind when you think about how the finite state machine is going to use these values to operate its state machines internally when we get over to that code. There's a bunch of math here so that I can write the code below without putting expressions like this buried in the middle of my combinational logic, making it harder for me and anybody else, I presume, to understand or follow along. I'll leave it as a task to the viewer to go through and read, make sure that the horizontal count maximum value, and the farthest right pixel is in fact the sum of the sizes of all these things, right? The left and right border, the active display pixel count, the front porch, sync, and back porch, right? So these are basically the same as they were before. I need to define counters. Need to know how many bits there need to be in those counters. I talked about this before. It's the ceiling of the log2 of these values up there. I think I talked about this when we talked about the vgasync generator. If you're new to Verilog, be careful. The problem is I want to be able to use these as variables down here in my ports. So they needed to be defined before we get to here. Therefore, they can't be local parms down here. And not that, well, you can't put a local parm physically in the file above, but these can't refer to local parms down here. All right? They can only refer to something that's already defined as a parameter up here because they're dependent on, stuff that comes in that's specified when we instantiate this module. For whatever reason, the philosophy in Verilog was not allow me to use a local parm, reference a local parm down here. So these are parameters for that reason. These are not supposed to be overridable. I think this is a language flaw because I didn't want to put this monstrous equation here, okay? And I don't want to let anybody who overrides this module to diddle with these things. You could, but that's not why these things are defined. So this is a one strike, yet another strike against Verilog, their philosophy of how this stuff has to fit together. All right, so that's why they're here. They're not supposed to be overridden. These are all the same things we saw before, plus a few other little ditties. Now the VDP, remember, has a text mode and it has various graphics modes. If you look very closely, when we're in graphics mode, you have an 8x8 square for each one of these. I'll call it a character, but these are the patterns, right? In the parlance of the VDP. In text mode, the pattern is only, it's going to be 8 columns by 6 wide. So it doesn't tessellate perfectly. It turns out there's 2 columns left over when we're in text mode. So the width of the active display region doesn't match the same size as it does when we're in graphic region. So in order to make it simpler in the finite state machine, I went back here and I hacked up this timing generator to say, look, when I'm in text mode, I'm going to count differently than when I'm in graphics mode. So the bottom line is the borders increased by 1 pixel on the left and right, I think. We'll see that below. We saw the horizontal, vertical, same column and row and so on before. These last jobbies here, I don't recall if I outputted them before in my color bar generator version of this. I added these because I might have wanted to use them in the state machine so I know when I'm done with a column or I'm done with the last row and so on. So these are there for reference if we want to use them in the state machine. What else do we got? Video active and video active 0. So this is the beginning of things getting ugly. Now, I should have gone back and refactored a lot of code as we'll move forward and look at how sprites work and stuff. The finite state machine started getting ugly. It's a different video. We'll talk about all that fun stuff next time. And I found myself wanting to know certain things that are going on inside my the vgasync. So like I said, I just started adding things that I wanted. Okay, I got video active and I got video active 0. Video active, since that I don't think was something that I had in the regular VGA color bars, maybe, I don't recall. Video active is true when the columns and rows are in this active display region, okay? Now, video active 0, we'll see down below at the bottom of this module that it is true when the next clock tick, the next pixel clock tick will make video active true. So this gives us one, T-1. It's 1 clock period early advance notice that in the next clock tick, this will go high. Okay? Sprite tick is a signal, it poorly named, it doesn't match these. We'll see this goes high 1 early, just like this active 0. Again, I probably need to clean this up, but it works, and I'm moving forward with this. We'll clean it up some other time. I don't have time to finish this and clean it up. There's only so much lifetime to live. So this is an example of my sloppiness during the evolution of code. And then, you know, again, we can look at cleaning it up later. And I'd like to hear opinions how better to do certain things. Because, you know, I don't know everything. And some people that view my channel, I know, have a lot more experience with some of this stuff than I do. So if there's a great technique out there, I'd love to hear about it. Anyway, moving on. This goes true when the next pixel clock, this is like my point is, this is a T-1 kind of a signal. So in my laughing at myself suggests maybe I should have put a 0 in there. But in any event, this goes true to let me know that the next pixel clock will represent a time period that would be optimal to start fetching sprite data. And sprites are a whole video on their own. I don't even think I finished the code yet, but I do have the analysis logic in the state machine to go out and get all the data for the current row and all that fun stuff. And I needed to know from the timing system a signal that said this would be a good time for you to start getting your sprites in order and analyzing which of the 32 sprites are going to be visible on this current pixel row. On the current, remember, these are all expressed in VGA pixels, okay? This is true when there's a border that's active on the screen. You know, when I'm in this region here, and you can, in your mind, hopefully that will flash a thought that says, you know, this is going to probably be a signal that goes into a mux, or a simple one of those question mark operators, which is, you know, a 2-input mux, a single bit output that says, do I put the border color on here, or do I pass through logic that is rendering the pixels of a pattern, okay? And that's what's going to happen when we get over the FSM. That's what that signal is going to be used for. It says what am I going to print? Just throw the border color on there, or pass through my current pattern pixel dots. This down here is going to be true, as you'll see one tick at the very end of a frame, and this is going to ultimately be the signal that sets the bit in the VDP. If we go back up here to the registers, register 7, our friend, that's the thing that turns on the frame flag. Okay, now I decided to emit that. We'll see end of frame if we just do a little quick search in here. When does this thing get set? It gets set when the horizontal counters, the next horizontal counter is going to be 0, and the vertical counter next is VBB begin. I want to point this out because it's not necessarily where you think. What do we got? Horizontal next is 0. So that's when I'm over on the left edge. And the vertical counter is the bottom border begin. Now, that means it's going to go true right here. Now, in terms of time, remember time is expressed in terms of pixel periods. So what I'm going to do is I'm going to set the end of frame marker. I'm going to turn on this frame flag down here. Remember, this is the reason this even exists, is to be able to generate an interrupt, provide a status information to the CPU to say this would be a good time to redraw all the data if you want to for the next video frame. Because remember, the thing that the user sees is here inside this region. And as long as it's not painting in this region, starting here rather than say down here, or you know, when the sync goes through, I've got all this extra time from all the bottom border, all the time that it takes to do the porches and all the other stuff, and the whole top borders, all that included, before anyone's rendering any pixels that we can see in here. That gives us as much time as possible, and early, I should say, as early a warning as possible, within reason, to the CPU to say this would be when you want to diddle with all the patterns and the color tables and all that stuff, okay? So I could have made it true over here. I remember going back and forth in my mind when I did all this fun stuff. If you want, you know, a partial row of pixels, which is a pretty small percentage of time in contrast to all this other time, you could tweak the horizontal counter value if you wanted to. You'd have to then also pick the right vertical counter that you would probably want to be VBB begin -1, right? You turn it on the prior row if you waited until the right border was active. You could probably set this to something like the right border and this to BB begin -1 if you wanted to get that much earlier. The problem with doing it earlier is that you have to be careful about where your sprites are. And I didn't want to think all that out, and I just said, okay, this is a sledgehammer on terms of timing there. I suspect because the way the pixels work is you always specify the upper left corner of where a sprite is, I should say. You specify the upper left corner, so as long as the upper corner is, on the right border of the last row, or greater in terms of which row number it's on, it's invisible. You do have to be careful up here because it could be rendering sprites that are real big. Remember, they can be, 16 rows high, which in VGA pixels is doubled. So that would be 32 rows of VGA pixels high if its upper corner is way up here and it's really big and the bottom of it's dipping into the display here. So in terms of what you can update and how much time you have, you got to take all that into account when you get there. In any event, this is a pretty reasonable time to assert that signal in terms of certainly better up here than way down there. Okay, that's all I'm saying. Okay, so moving on, what else do we got in here? Other than that, the code in here is going to be very reminiscent of what you saw before. I'll leave it as the test of the viewer that's following along to verify all this and how this stuff all works. It's the same as what we saw before, but there's obviously more of it. I wanted to be able to create a bunch of variables again so that in the main combo logic below I can use these things instead of giant equations that we don't follow along and harder to debug and all that fun stuff. Here's the text mode padding. Make the left and right borders this much wider in text mode. In my mind, I remembered I was off by 1, but apparently I'm off by a bit more than that. Like 2 whole pattern sizes for each of the left and right borders. Again, we'll see that down below. The usual state machine stuff. Compared to the bar generator, I just have a few more things to keep track of here. Namely the borders, whether or not the thing is visible and whether the sprite tick is supposed to go on to the next round. But otherwise, the same kind of a thing. Here's the VC and HC bits down here to match the parameters above. Zero everything on a reset. Propagate the next state through every time we get a clock. And remember, this is the VGA pixel clock, not the VDP pixel clock. I can't punch that enough. You'll get confused when we get over the state machine if you don't start thinking about that now. I threw a note in here to make sure I hit this. Remember, it's actually okay to start with junk in here after a reset. And I do start with junk. Setting everything to 0, as we just saw 2 seconds ago, means that the first thing that it's going to output is way up here, and no VGA screen is going to be able to start emitting video and know and understand that I'm emitting video up here until it sees its first real vertical sync. It can't know what the data means yet, or what row it's supposed to be on. So it would probably be better if I started down here instead of up there. I mean, I could just set it to a row down here. But you'll also know that certainly any non-glass screen waits for a few frames to go by before it even shows it. I personally find that mildly offensive. I would think it would need only one single entire frame to analyze the timing, to know what mode it's in and all that other fun stuff. After that, what am I waiting for? I never could understand why TVs and displays take forever. I mean, yeah, maybe they don't want to glitch around. Okay, great. But just get it on the screen. I don't like it when it takes literally like multiple seconds on some monitors to do that. Whatever. Okay, great. So I'm basically wasting an entire frame of time is my point, because I'm literally starting up here in working my way down. It helps me understand the waveform for debugging, and I know the monitors take forever anyway, so who cares whether I start up here or start down there. So, moving on, what do we got? The usual stuff here where I propagate the default values into the next values here, okay? This one obviously is going to be conditionally reassigned down here somewhere. V counter next, yada, 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 equals that, da, 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 da. Where does he get it set? Oh, it's right here. So why didn't I do this like I did all the other ones? I don't know. I just wanted to be inconsistent to make sure that everybody, keep everybody on their toes. And by that I mean literally all I need to do is assign all these, and sometimes there's a question mark operator, sometimes there's not. This one I use an if instead of the question mark operator, but this is the same kind of a thing as we saw before with a regular old VGA color bar generator. You know, am I at the end? Reset it to 0, otherwise go to the next one. So those are your regular pixel counters. The video active, I got to ask, am I in the region and stuff, right? And this is where text mode comes in. I say, look, if I'm not in text mode, I'm just, you know, as long as the horizontal counter, the column counter, is greater than or equal to the beginning column, I must be in an active video region, and less than the end of it, right? So that'll work fine. And what do we got? And the vertical is left. So what happens here is, as long as the count range is for the column is greater than the left and less than the right, I'm good. But I also got to ask, am I on a row that's supposed to be active? Don't make the video active be true down here, okay? That would be bad. So I have to also ask about the vertical counters. Make sure that is in the visible region as well. The text mode has to do with, as I said before, this thing is going to go active. In this case, instead of going active if I'm greater than vvid, hvid begin, it's going to be hvid begin plus the padding. So the padding fits on the left here. So I got to make sure that it's in, a little bit further to the right because there's extra columns here that I'm not going to use. Same with over here. These border will creep in on the left and the right when I'm in text mode. So that's what's happening here. I'm going to say start a little bit later to, same as I would, but wait a little extra for the text mode padding, and end early. Instead of ending here, I subtract it off there and end it a little bit early. The text mode is the same height as regular graphics mode, which is why there's no special logic here. Now, visible is different than active because visible is visible. That includes the borders, all right? So that logic is basically the same, but it's based on the whole visible size as opposed to the active dimensions, right? So what do we got here? It's greater than or equal to the visible begin, which is going to be like 0, I'm sure. And the horizontal counter is less than visible end, and the vertical counter is greater than that, which will be 0, and it is less than end. So what we're doing there is we're saying, am I greater than 0, 0, and less than whatever the coordinate is down there, okay? Which is going to be 640 by 480. Okay, what do we got? Border. I'm in a border if it's visible and it's not active. That should make true, and that's also next. So these are, remember, these are all the next signals. After the next pixel clock, the border is supposed to go true. Horizontal sync, vertical sync. We saw that before. This is the same as before. If I'm in the right horizontal, range of columns or vertical rows and stuff, assert the vsync and hsync. Sprite tick. Perhaps I could have come up with a little bit more clear name than sprite tick, because that suggests that maybe I'm drawing a sprite pixel or something. What that is the sprite fetch logic I talked about before. That works the same kind of way as the idea with the the frame flag. I'm done with my active display flag. This is a tick down here is going to go true. It turns out it's going to go true over here somewhere. I can't remember how I set it up. We'll see that soon enough. And what that means, actually it goes true right over here on the left. Okay, and the reason I do that is because I know the row counter has a value that represents the row that I'm going to draw. it goes true over here because this amount of time in terms of pixels can be used in my finite state machine. That's more than enough time that it takes for me to go out and look up in the memory to find the sprite attribute table and the pattern table and the color table and all that other fun stuff to figure out which sprites are going to appear on this row, where they're going to appear on the row, and what colors and the pixel patterns they're going to have. Okay? And if you think about it, I got to scan through all 32, up to, I should say, 32 of the sprite attribute values in order to find the first 5, or the first 4, I should say, that can appear on the row, because you can only have 4 on a row on the TI VDP. The 5th one is supposed to be known because we want to put the 5th sprite number that could appear in here. You know, for full compatibility, that's what we want to do. If we really wanted to, we could probably draw all of them on there. If we wanted to, that would require us to have enough time to go out and fetch all 32, which we do have it. We'll see when we get there in the state machine. There is more than enough time to scan all 32 of them. There may not be enough time to render all 32 of them on this particular FPGA. We'll look and see what the pros and cons of how I'm going to go about doing that works later. That has to do with the size of a priority encoder, and the propagation delay through that encoder will dictate the practicality of how many of them we can put in a row. Okay? In any event, the point of that signal is it goes through to let the state machine, this is one of my add-ons, it lets it know when it can start fetching all the sprite attribute data and stuff like that from the video RAM for the current row. So what do we got? A vertical counter is greater than VVid, which is probably the active. No, that is visible video. And the reason it's not active, remember, as I said before, pixels that are rendered up here can have the bottom dipping into the display. So it turns out that I actually have to check the sprite data even when I'm drawing these borders up here. So what does he do? If the visible region is true, if I'm in a visible region and the vertical counter is less than the bottom of the screen, so this is a little excessive. It means that's going to be a bigger number than it really needs to be, but it's okay. It just means that the VDP will be fetching sprite data, even though if it does render them, it'll be blocked, because that means that the sprite might appear down here. Okay, which, you know, who cares, as long as we have enough time, bandwidth on the memory to do this. It doesn't matter if it does that extra, or we can tune this later when we optimize our code. And what else we got? Horizontal counter next equals the begin, and that basically means, you know, column 0, right border begin. What am I doing? HRB begin, horizontal right border begin. He's doing it here? What? Well, let that be a foreshadowing to the state machine. I may have done some optimization over here. I find it strange that I would have run it that early. And the reason I'm pausing myself is because if you start searching for sprites, starting here for the next row, then what happens is that the current row counter that comes out of the vgasync module that we're looking at will be the previous row than the row you want to look at. So when we get to the sprite stuff, we'll probably see in the state machine that I need to add 1 to the row number I'm on, because if I really do set that true here, it would be good to do so, right, if it does work, because it gives me all this extra time during the front porch and back. Same argument about setting the frame flag up here instead of down here. It gives me extra time to diddle around with the memory to get the sprites ready. All right? And I stutter because I would swear. I haven't looked at this in a while, a couple of weeks. I swear I said it true on the left side of the screen, not the right side. But that's fine. I give myself extra time here. We can have a look-see at the waveforms in a little while, and we'll see this signal go true to double confirm all that fun stuff. So the rest of this is the same as it was before, plus, you know, your border active and stuff like that. We already talked down here about what this means, and the column and row last. True one tick before it changes to 0. True one tick before here. So these are true during the last period of, you know, the final column on any given row and the very last row before it goes back up to 0. And at one time, I'm sure I needed this in the FSM, or I might still now. Again, I can't remember all the details over there. But I kept on, my point is I kept on adding more stuff to the vgasync when I felt it was better for this guy to generate it and send it to me on a silver platter than add it to the state machine logic. Now, to test this, what I did is I made a vgasync test bench right here. And the way you run it is just type make vgasync. I'm trying to kind of standardize how my test benches work in this project, where if I have a module called vgasync, there's a vgasync.v, and then there's a vgasync testbench.v, like these guys down here. And in the make file, you type make vgasync to run the test bench for that module, all right? I'm converting over to it. I think I did a massive walkthrough of all my code and made that happen earlier this year. So if you want to know my convention, that's what I did. Now this is going to be an artificially small set of screen dimensions. Why don't we go ahead and take a quick peek at what that is. Let's background this. And here, okay. I artificially overrode, look at it, I got the vertical active video region, 5 pixels high. Right border is 2, front porch is 2, horizontal sync is 3. These are super tiny sizes, all right? And the reason I did that is so that I don't have, you know, 8 billion, well, not 8 billion, but probably 1 million pixel times on the, or about 500,000, in reality, 640 times 480, plus all the bordering stuff, just on the order of 1 million pixels, okay, to represent all the time of an entire screen. It makes it easier for me to see what's going on. And what do? I just generate a bunch of clocks. I set the reset. I undo the reset. I say, just wait a long time and then stop it. I have since, as we'll see in the bigger picture, my test benches actually can be more interesting. I didn't use it in this case. What I could have done, for example, is waited for the frame flag to go on down here. I could have waited for a positive edge on the frame flag coming out of the vgasync generator instead of hard coding this, so that that way when I change the the values up here, if I decided to do so, it would then just run longer in order to do an entire frame. Okay, and I get better at that as I go. This is just a quick hack to be able to test my vgasync, and I go in here and I just bash around these values at my will to test various code changes from time to time. So what do we got here? Here's the whole picture and multiple screen loads. See the vertical sync, tick, tick, tick. So this is many frame loads of time. So let's just zoom in at the beginning here and have a look-see. What do we got? Vertical sync. So this is actually, remember when this thing boots up, when it gets a reset, it starts up here. There's my vertical sync time. So if we start up here, we see the vertical sync, and then we wait for it to go around again. We're getting the whole picture here, right? So this over here, for example, you can see this is my vertical, this is my row counter value here. It starts at 0 because I reset it right there. There's my reset signal, which makes everything, the row horizontal and the vertical counters go to 0 and all that other fun stuff. What's going on down here? This is the visible next and video active output ports. This thing here is true, remember, on any row and any column that is merely visible. So that's this region out here. So it should go true from here to there in the horizontal, for each horizontal row. And because I got this artificially few number of rows, I only got like 3 rows in the visible space, and 4, 5, 6, 7 total rows. I should say 3 in the active space, 7 in the total visible space here, right? Then down here, what do I got? I got 1, 2, 3, 4 rows that represent the front porch. Here's my vertical sink. My vertical sink is 2 rows, 1, 2, 3 rows in the vertical back porch. So that bottom stuff is these 3 guys. All right, and we can go back and look at this to double check that, right? So the vertical front porch is 4, vertical sink is 2, back porch is 3. So you just saw 1, 2, 3, 4. You got your 2 and your 1, 2, 3. So these all match the desired values. So, and I got a lot of mileage out of this when I was tweaking around and playing with it. Here's a little sprite tick jobby, so we can now see where that goes true. It goes true, where does it go true? It goes here. What is that thing? That's the video active. So it actually goes true, like we noticed. This is my actual, it's video, it goes true on the last active pixel, so that this rising edge of the pixel clock up here means that the first time the state machine will start looking for pattern data will be right after the visible active, I should say, region of the screen is over. So, wow, a good thing that I review these things. Probably should have reviewed it a little more before I talked about it, but I moved it up to the previous row is my point. That is what's happening, and we saw that in the code. So when we're done with, row number 5, we assert the sprite tick over here to say that this is when you should start looking at the pattern data for row number 6, the next row, okay? So that's fine. It just gives us a little bit of extra time to do all that work, okay? And the rest of this works just the same way as it did on the vgasync thing. So what happens at the end of a whole screen, right? We should see here's my column last, right? At the very last column of any given row. That should go true here. This is the sprite ticker. We just saw that. And you can see it goes true before, on the row before that were active over here. And this might be kind of wonky because this screen is so artificially tiny. We should look more closely to make sure that the sprite tick goes true at least 16 rows before the first one, or I should say 15, because the magnified sprite could have a single pixel dipping down into the active display here if we have an origin up here. Now, in this case, it does go active early, but the screen is so small we don't know, given this particular test bench, whether it will go true at least 15 times 2, because we're in the VGA coordinates here, not the VDP ones, right? So it needs to go at least 30 pixels high earlier before the active part of the screen. We can do a bigger one with actual parameters in a minute, and then we can take a look at that. You'll see it's a bit more busy, but just to verify that that is configured to do the right thing when we get there. So what I'm looking for here is the frame flag. Where is the end of frame? He goes true here. There it is. So he goes true at the end of the last, or the beginning of the first non-active row, which is what we saw in the code. That means he goes true over here after he renders the last active row. So that looks good as well. All right. So what did I miss here? What's this guy doing over there? What's this one? row last. Okay, there's the tick that goes high for 1 pixel before we flip back to 0. Okay. This does work because I've been playing around with it quite a lot, and it does go. That doesn't mean it's right, so I welcome any constructive criticism on this thing to cut down on my own frustration. If you want to debug it, knock yourself out. Now, if you want to work ahead, this vgasync. The next thing we're going to look at is this state machine over here. This is a big, messy code. I'm not at all proud of the state that this is in, but it works. And I want it totally done before I start refactoring. I've been doing some refactoring, but I'm, kind of concerned, like I already alluded to, me messing around with vgasync, adding some more signals out of there. So before I go and re-clean up everything, let's finish ruining it first. I'll do a cleanup down the road in the future, or I will leave it as a task for the user. One way or another, this probably should be cleaned up. Anyway, our next step is to look at the state machine. This test bench, if we look at it, if you want to work ahead, has an assertion in here, and this is a false assertion, and it just shuts itself down. This test bench is really only useful at this point to make sure that you can just simply compile the state machine code. This test bench is currently pretty useless, okay? Don't use that one. That's why I'm pointing this out. If you want to work ahead, go over here into the main. This is where the top level code is for the Z80 Nouveau peripheral stuff with the VDP 99. Run this test bench here. This is, we'll have a look-see at it right now. Why not? Let's run the VDP 99 test bench that represents an entire frame of the VDP running with the vgasync and everything else in the entire system. This is the entire system running in this one for a full frame, okay? And I have a dump of the RAM that goes in the video RAM here. It loads this in. Let's take a quick look at this test bench before we get into it. This one has, everything, fire all the guns at once here. Is a fairly complex text bench, and I talked about the style I use in here on the channel before. I create the entire VDP here, which has nothing but the CPU bus on it and the colors coming out of it, okay? From the CPU perspective, we got the clocks going in here, and I have this funky special loop. I talked about this before, which is each time it goes around this loop, what it does, it does an entire register a whole register read and write transaction from the CPU's perspective, and it spins around this whole thing and does all that. Because each time we interact with the VDP from the CPU, we need to do the same thing all over again. I'm using this as if it were a subroutine. And what you'll see in here is it waits for the write signal from the CPU to come along to say, I want to write to a register, and then it diddles around and does all the waveform stuff as necessary to make that happen, okay? And this is triggered down here every time I get, let's just take a random area. We say, here's the register 5, I want to put that value in there, and I set this thing to a 1, and then I wait for someone else to turn off this signal. Well, this is me turning it on and waiting for the loop we just looked at to turn it back off. And then I can move on from the perspective of the CPU, and I can interact again and so on, all right? So that's how you read this fun thing. And in here somewhere, where's the right there? There's this loop, there's the bottom of that loop, turning it back off, and it'll wrap itself up, wait the appropriate number of time for the CPU to finish its transaction. And I got this thing all the way down to the right number of nanoseconds and everything. We can look at this more closely, if I haven't already, when we get heavily into the finite state machine. So anyway, if you're going to do this, what you're going to see is I write a bunch of stuff into the VDP registers from the would-be CPU in here. And I used to play around, a couple of different debug things going on in there. Then what happens is I wait until vgasync goes on. Remember, I'm going to start up here, so it's going to run all the way down here until this thing goes on, right? When the CPU is writing all those configuration into the registers, it'll finish it by the time it gets like right here. I mean, it's going to go real fast by the time this first row is even done, okay? Because it's only going to do a handful of register writes. It's going to be a couple of what is it? Each time you write a register, it takes 2 I/O cycles from the CPU, which is a few dozens clock signals in the pixel domain, the pixel clock domain. So we wait until the sync goes on, then we waste a little bit of time, and we make sure that the interrupt request signal comes back. The end of the frame flag goes on. We waste a little bit of extra time. What are we doing here? And wait for the IRQ to go off. Then we reach in. I'll talk about this more later. This is me reaching way into the vgasync module, because why did I do this? Second frame to begin. It wants to wait. Yeah, what it's doing. So we start up here, we write a bunch of values out while we're drawing the border. Then it does a whole frame, it waits down here, and because it's waiting for video active to go on again a couple of times, what it's really doing is it's waiting for a few rows to go out in the next frame. That's what it's doing, all right? And I reach way into the VDP 99, and I access the video active variable that's inside that module. If you haven't seen this notation before, in Verilog, you can just reach right into the middle of a module using this hierarchical path. The VDP, it's top level. I called it UUT, and inside the VDP 99, there's the what is it? The vgasync is in there, and some other things are in there. So that is what it's called inside the VDP 99. There's a VDP in there, and there's a finite state machine in there. So I can reach in and grab values if I want to using a path. That's what's going on in there, right? So anyway, I wanted you to get an understanding of what you should see if you decide to say make the VDP 99 test bench. It takes a little while, and I dump a lot of debug stuff out. This is a bunch of junk that has to do with the sprites. You can see it's saying, I'm looking for sprite number 0123. It took a long time to run, okay? That's because this screen, it won't even fit on this. This is going to have so much stuff on it now. I spent a lot of time looking at this when debugging. Now, the unit under test, what I'm creating there, remember, is the this thing, okay? And this thing inside there has the VDP 99 in it. So this is the Z80 interface, and I've talked about this before on my channel. This is the interface between the Z80 that hooks onto the VDP 99, and then inside here there should be a VDP 99 that's called the VDP, and that's why you have that path, right? And we talked all about the VRAM sizes and all that stuff, because we don't have enough memory for it all. That's where this comes in, right? So that's why that is there. So the question is, what do we want to see? Do we want to see what's in the Z80 thingy, or do we want to see what's in here, or both, or all of the above? So if we go to VDP, this is the VDP 99 module that is in this directory. That's this guy here, which we just ran, which we have also seen before. It's got the register interface in it, the interrupt request coming back, all this fun stuff, all the junk about the VRAM and all this fun, the DMA interface and all that stuff. We're going to see this go nuts when we go into the finite state machine. We'll see how all that stuff works. Here's your vgasync here. That is what we're looking at. And you see the signals coming out of there, going into the finite state machine down here. And you can recognize all the usual suspects in here. The DMA stuff has to do with it reaching in and diddling with the memory. We talked about the memory before, but there's a little bit more to the memory than we last talked about. In here you should see a memory synchronizer module somewhere in here. Memory, VRAM out, DMA tick. Where is it? I'll have to dig that up. It might actually be inside the memory module itself, the thing that I'm thinking about. There's a special timing case that we have yet to talk about that has to do with talking to the memory, but we'll get into that when we get to the state machine. Anyway, my point is, if you want to work ahead, this is the timing stuff you want to look at. What am I going to do? I want to say, take all these, add it to my screen. Now, there's going to be a lot of stuff. And what do we got here? Here's the sync, vertical sync right there. These are all the rows. And what do we got down here? There's the VDP status. Oh, that's the, yeah, that'll be the status register. The 80 down there, this is register 7. That's why the frame flag is on. That 80 is this bit right there, the most significant bit. Okay, so you see that frame bit go on there. What do we got here? Here's the IRQ tick. This is the thing coming out of the state machine that we were talking about. It's called IRQ tick in the context of this guy here. There's the last pixel. Last pixel is what it was called, remember, in the vgasync, but it becomes the IRQ in the context of the interface to the Z80. And you can see that it goes on in register 7 here. It goes back off here because in this particular test case, you'll see that somebody reads. You zoom in and look at the, what address is on the address bus from the CPU at this time. It's reading register 7 there. That's why it goes back down here. vsync. So there's my vertical sync, and here's all my rows. So what we should see happening is buried in here, the sprite tick stuff, and that's why I zoomed in here. There you go. It's this row right here. Let's turn on my wave highlight. So if you want to work ahead, you'll notice that this little sprite tick jobby goes on. Now this is the full size. We should see it go on in a reasonable amount of time. There may be a bug in my code here. It goes on here. It goes on early because it goes sprite. This is a good time to grab your sprite data before it gets to this next row. Okay, so you do see it here, and then down here, when we look at the VRAM, this is the state machine that we'll look at next time, interacting with the memory. And there's probably a big scroll bar over here of all kinds of other stuff going on. There's the address going into the memory, the read tick signal we talked about when we were talking about the memory, the column and the row, the border active, and all that other fun stuff. So what I'm getting at when I said I think there's a bug in here is this sprite active goes through for the first time way down here for row in hex 30. And because I was talking about before, if I've got a sprite up here whose bottom reaches into the display, I need to start checking sprites way up here, not down here by the active display. So there is a bug we just found. So it's easy enough to fix. I just have to change the value of, here's the first row that I need to start fetching sprite data on, and make it earlier in the video frame. All right. So this is a useful little little test bench if you think about it. So there it is. It's going and checking all our fun sprite stuff. We zoom in on any given random row here. You see a lot of memory interactivity right there. And what it's doing is it's fetching it's walking through the sprite table, starting at the first attribute, looking for the sprites that are enabled for the given row. So it may, or this will take a variable length amount of time, up to 32 attribute loads worth of data. And I don't remember how much, as I record this right now, done in terms of the sprite code. I don't know if it's actually reading all the attributes and the pixels or not, or if it's just reading the attributes to figure out which ones are visible on the current row, after which, either during which it will read all that other data and hold on to it for the row, or it'll do it over here. I don't remember how far I am in there. But I do remember adding up all the time and saying, in order to get them all on, I need so many pixel periods of memory accesses that I need to be able to do. So I don't think that I can finish it if I wait until over here was my problem. Okay, so I decided, what do you say we start as early as possible? That I do remember messing around with. So we're in a state of incomplete implementation for the sprites, but all of the other stuff, the graphics modes and the text modes, are done. And if you want to look ahead, you can get a good view at all that fun stuff in here. And this, of course, is the final product of everything that's going on here, right? I don't know, what's a little bit of stuff, test cases over here. Oh, this is it waiting for the next frame to start in the logic I just went through in the test case to make sure that when it's done here, I get to see it all the way into the next active display on the screen, and you can actually see the sprite tick starting to go off again. Again, not early enough. Oh, wait a minute. What do we got here? What is happening? Video active. As opposed to visible. Where's the visible? Yeah, you can see here, okay, the sprite tick starts firing here. I'm wasting all these are the border rows. Here's the border active. You see how they're wider than they are over here? Because this is the left, middle, and the right. All the whole top border is the full length of the screen, right? That's this whole time in here. But when I'm on a row that has some active display, it'll go on for a little while, then off, on for a little while, and then back off. So by looking at this up here, we can clearly see that I got a bug in terms of when to start getting the sprite attribute data. I only do it one row in advance. I need to do it 32 in advance. 32 VGA rows in advance. So I don't know, where's my row counter? Here it is. 2F, yeah, this is, I got to start it at the beginning of the whole screen. So, yeah, it should start it way over here, which is fine. I just used the wrong row. Why don't we go ahead? We're in extra innings on this video anyway. Let's see what I did wrong. And, oh, yeah, always good to do this while recording. VGA sync. When I decide when to start looking at the sprites, it looks like I might have just hard-coded something. Sprite tick vertical counter is greater than, yeah, I shouldn't have done that. And I think I mentioned that at the beginning. This probably should be more like greater than or equal just 0. Is that true? Well, this will affect how the state machine works, is what will happen. Because the question is, what is the state machine expecting? Does it count its own rows out or not? How is that all going to work? Because we'll talk a lot more about this when we get to sprites. And when we debug it, that one thing that will definitely change is when we have to start looking at when we start looking for the sprite attribute data, because I know that the height of these things can reach down into the active display from up there. Okay, so again, if you want to help out, feel free to chime in. For those of you that watch the end of the video, I'm pretty sure this is wrong. We'll see that happen when we get there. So, as always, thank you very much. Thanks for visiting my shop. I'll see you next time.